All right, so in this video, we're going to talk about the graphing process and then actually look at a few examples. Every instructor, every textbook has their own quote-unquote process that they want to have followed. Mine is very, very simple in respect to a nice logical way of showing your work and keeping things organized all the way up until putting the graph together. So hopefully this goes well for you. First things first, hopefully no surprises. Always the domain. You can't really move forward very well without identifying the domain of the function. The second step would be to understand the end behavior and study all asymptotes. I think I spelled that wrong. There we go. So study all asymptotes. And now, not all functions will have asymptotes, obviously. But when it comes to the end behavior, excuse me, and the asymptotes, both of these need to be done using limits. So in college algebra, many times you were just told to memorize some things, or you were told that this happens and not really given any explanation why. Now we're to the point where we can justify both the end behavior and the asymptotes using limits, and so that's something that I would be looking for in each of these. The third step then would be the first derivative test. And if you remember, that first derivative test is going to give us intervals of increase and decrease, as well as relative maxes and mins. The fourth step would be our second derivative test. And if you remember from the last video, the second derivative test, much like the first, is going to be giving us now the intervals of concavity as well as the inflection points, right, where the concavity changes. And then the fifth step here would be to find the intercepts, and meaning x and y. And then the sixth part is to actually put the graph together. So we'll use this process for each of these examples. I'm sure my math lab will kind of walk you through the parts that they're looking for in their order. But when it comes to the written work, this is what I'm going to be looking for as well. All right, so in our first example here, we're going to take a look at an x to the fourth minus 3x cubed plus 3x squared plus 1 function, and we're going to go through the entire process. All right, so step one, remember, is to find the domain. This is a polynomial, so the domain is going to be negative infinity to positive infinity, no questions asked. The second step, this is where we talk about the end behavior and the asymptotes. Now, a polynomial is not going to have any asymptotes, so I don't have to worry about that, but I do need to worry about the end behavior, right? So where does this function start? Where does this function end type thing? And so that would be us investigating the limit as x approaches positive infinity of the function, as well as the limit as x approaches negative infinity of the function. Now, if you remember back from when we studied limits earlier in the course, each function has a dominant part. And in this case, the dominant part would be this highest degree term right here. So for a polynomial like this, the end behavior of just the highest degree part will be the end behavior of the entire thing. Back in algebra, we called that the leading coefficient test. But in calculus now, understanding how limits work at infinity, this stuff is not going to influence the overall dominant part like it is here. So when we talk about taking a really, really big positive number and plugging it in right here, that's of course going to spit out a positive infinity. When we take a negative number, like a negative 10 billion, and we plug it in here, it doesn't matter, it's still to the fourth, therefore we're going to be moving into positive infinity again. So that tells me, when I look at my graph, that as I approach positive infinity, my y is going to positive infinity. So my graph's going to be doing something like that. As I approach negative infinity, I'm still going to positive infinity. So I'm going to have something that looks like this with all of the other stuff happening in between. So this is the end behavior and end behavior of our function. Okay, so now we've got the step 2 done. Step 3 was that first derivative test. So our f prime would be the 4x cubed minus 9x squared plus 6x. We would take this, we would set it equal to 0, and we would solve it for x. Now, when you solve this for x, you could factor out an x, of course, and that gives us a 4x squared minus 9x plus 6. And this guy here gives us the x equals 0. This other part, not to waste your time in the video, but you can solve this using the quadratic formula or by completing the square, but it spits out imaginary numbers. We don't care about imaginary numbers in calculus. We want to study real numbers. And so this is not going to come into play. I'm just ignoring the part that gives us the imaginary solutions. So this would be our only critical value going into that first derivative number line. So just like our first derivative test in the last section, I'm going to go ahead and put my 0 on here. I'm going to test numbers like -1 and 1. I'm going back into the first derivative. So I'm going back into this guy right here. You could go back into here if you wanted to as well, it doesn't matter. But when I plug those red numbers into the first derivative, I get a negative there and a positive there, which means we are decreasing from -infinity to 0, and we are increasing from 0 to positive infinity. Since we change from decrease to increase, we have a relative minimum at 0, f of 0. Remember, to get that y coordinate, we would go back into the original function. So there you go. There's the first derivative test. Now, we move over here, back to the top of the screen. Step 4 is going to be that second derivative test. So this is where I now take the second derivative, and if we take the second derivative of this guy right here, that's going to give us our 12x squared minus 18x plus 6. And we're going to do the same thing we did for that first derivative test. In our last, in that last discussion, we talked about where that derivative, second derivative, is equal to 0, where it's positive, where it's negative, and how it gives us those intervals of concavity and those inflection points. So I'm going to take this, set it equal to 0, and when I solve this for x, I'm going to get an x equals 1/2 and an x equals 1. Now I'm putting these on my second derivative number line. So a 1/2 and a 1. And then I would test values like maybe 0, maybe 3/4, and maybe a 2. And because this is a second derivative test, I would take those red numbers and I would go back into the second derivative. Okay, so chances are I didn't show my work here because I'm trying to keep the video somewhat efficient. I'm assuming people can handle the algebra, the factoring, but this looks like it should have factored from what I did into 2x minus 1 and to x minus 1. I do want to show you though that because of how it factors, when you take these red numbers and plug it in, I wouldn't go into this thing. I'd go into this right here, and you're only searching for positives and negatives. For example here, when I take a 0 and I plug it in, when I take a 0 and plug it into this first factor, I'm going to get a negative. When I take a 0 and plug it into the second factor, I'm going to get a negative. Well, the negative times the negative is going to give me a positive. So really, no actual number crunching needed. You're just going to determine the sign of each of these factors, and then knowingly, when you multiply them together, is the result going to be positive or negative? Okay, so again, nice little shortcut there. Didn't show the work, but it does factor, and you would obviously do that to come up with the 1/2 and 1, so take advantage of those factors. Okay, so to kind of finish the signs off, that was a negative, this guy ends up being a positive. And so, to summarize that, we are concave up from -infinity to 1/2, union 1 to positive infinity, and we're concave down from 1/2 to 1, right? Positive means concave up, negative means concave down. We also have it looks like two inflection points. The inflection points would be at 1/2, and then we'd also have another one at 1. Right, remember the inflection points where the concavity changes. We change from concave up to concave down here. We change from concave down to concave up here. So those would be our inflection points. To find the corresponding y coordinates, we would go back into the original function, so f of 1/2 and f of 1 for those. Okay, so that's the second derivative test. Again, not very different than the first derivative test, just gives us different information, and you'll see how that comes into play shortly. So when it comes to the intercepts, this is step number 5. Step number 5, intercepts. Just to kind of get to the chase here a little bit, in terms of x-intercepts, this is where we take the function, set it equal to 0, right? Let y equal 0, solve for x. In this particular case, there are none. You would come up with imaginary solutions if you did that. For the y-intercept, this is where we let x equal 0. When we let x equal 0 in our original function, you could see that you get the point 0, 1. Okay? Now, before I actually put this graph together, what I do, when I'll circle back here and talk about things that I will be looking for in the written work and how I want things labeled and shown. So a couple real big things. First of all, obviously you're going to have your domain, and make sure that's written in interval notation. So domain and interval notation. If this was a written work project, you would also show me this information right here for the end behavior. The third step being the first derivative test, I'd be looking for intervals of increase and decrease. And when I box in this stuff, obviously you would include all your work, but this is the type of formatting that I'm going to be looking for things. And then the points for the relative maxes and mins, I want written as whatever the value is, and then f of whatever that value is. You don't have to find this for me. In fact, I don't want you to find this for me. I just want to see it as the function evaluated at whatever the x value was. Okay. Similar on that second derivative test. Obviously, you would show all of your work, but this is the meat of it. The concave up, concave down intervals, as well as the inflection points, written the same way as I've written my extreme values. And then for the intercepts, what you see right here, you don't really have to write none if there aren't any, but when it comes to the intercepts, do write them as a point. Okay, intercepts are points. You got to write them like that. If you tell me y equals 1, well, y equals 1 is an equation, and it's also a horizontal line. So make sure to distinguish between lines and points. Okay, now I don't know that I've done the best job here of space management, but I'll do my best to get a graph up here now. So I need to take all of that boxed in information and now put it all together in a graph. All right, so when you graph something, x-axis and y-axis need to be labeled. And then when I put a graph like this together, I usually don't pay attention to all of the information given until I have a graph on my paper, and then I'll circle back to make sure it's correct. Sometimes information overload is not a good thing. So a couple things that I want to pay attention to. I know that my domain is everything. So when I put my pencil down, I should be able to graph the entire function before picking my pencil up. I also know that I'm going to put my pencil down in quadrant 2 and pick my pencil up in quadrant 1. So I'm going to start here, it's going to do something, and then it's going to end right here. Then I kind of use my increase and decrease as the best guide. I can see here that I am decreasing from negative infinity to 0, but increasing from 0 to positive infinity. That alone is some really good information. And then finally, my intercepts. Okay, again, I know I'm ignoring a little bit of this, so I'm going to circle back to it, but then I've got my intercept here at 1. So let's see what happens when I sketch this in. I'm going to put my pencil down, and here's 1, by the way. I'm going to put my pencil down, I'm going to decrease, and then I'm going to increase. And that's, again, provided I actually hit my mark, but you get the idea. Okay, so far, that's met, that's met, that's met, that's good, that's good. I've got my minimum, and I've got this, right? So this must be my graph. Well, again, this is actually what I would have done. I would have done what I did here, but now I'm going to go back and look at my intervals of concavity because this is not the correct graph, okay? I want to get something on my paper. I know the majority of it's right, but I have a little bit of something going on here with this concavity. So I can see that I'm very clearly concave up all the way through. but I should only be concave up until 1/2, then I go concave down to 1, then I go back to concave up. So it looks like there's actually going to be a little bit of a bulge right here, and then it'll go back up. So let me go ahead now and erase, if I can. Let me see here if I can do this differently. Yeah, let me erase like this. Okay? So here's our 1. So I am concave down, and then I have that little bit of a bulge, and then I go back to concave up. That's not quite as smooth as I would like it to look. So I'd concave down, and then maybe something like that. So here I would be concave up, concave down, concave up, where my inflection points right here and right here, this would be my 1/2, and this would be my 1. That's where I change my concavity. Okay, so feel free to obviously zoom in on that as needed. But yeah, there you go. Sometimes if you just take everything into consideration to start, it can be very overwhelming. As you saw, I don't always do that. And I came up with the incorrect graph, which is perfectly fine, because then I came back and I realized, okay, the concave up and concave down clearly is a part of it. So I'm going to have this little bulge right here giving me concave down from 1/2 to 1. So there's the graphing process of one example. Now that I've kind of explained it all, we'll look at a few more examples and hopefully be able to move a little more quickly through it.